In this videotape, we will introduce the idea of the square root of a number. We all know what it means to square a number. Okay, for example, if I say 9 squared, I mean 9 multiplied by itself twice, that's 81. 9 squared is 81. The square of 9 is 81. Let's consider now a reverse problem. Suppose I tell you that the square of a number is 9. What was the number? Okay, let x represent the number. The square of the number is 9. What is the number? Okay, certain number squared is 9. What must the number be originally? Okay, well, you can sort of reason this out. If x squared is 9, x could be 3, because 3 squared is 9. But it could also be minus 3, since minus 3 squared, minus 3 times minus 3 is also 9. Okay, 3 and minus 3 will be known as square roots of 9. In general, we will say that x is the square root of a if x squared equals a. X will be called the square root of a if x squared is a. So we say 3 is the square root, or is a square root, because a number can have more than one square root. 3 is a square root of 9 because 3 squared equals 9. We can also say minus 3 is a square root of 9 because minus 3 squared, which is minus 3 times minus 3, is 9. So the number 9 has two square roots, positive 3 and negative 3. All positive numbers will have two square roots. And the square roots will be negatives of each other. They'll be opposites. They'll sum to 0. Okay, we'd like to have a symbol to indicate the square root of a number. We're going to use a radical sign. Okay? The square root of 9. Now, we don't want to say this could be 3 or minus 3. We don't want any ambiguity. So we're going to say that the square root of 9, written like this is read the square root of 9, is the positive square root of 9, which is plus 3. And if we want to indicate the negative square root of 9, we have to actually put the minus sign in, and that will be minus 3. As I mentioned, all positive numbers will have two square roots, and they will be opposites. They will add to 0. Okay, the number 0 has only one square root, that is 0. The square root of 0 is 0. Plus 0 minus 0, of course, is the same. It's 0. Negative numbers do not have any square roots that are real numbers. We're only working here with real numbers. Okay, those are numbers that have decimal representations. Okay, real numbers. Okay, the square root of minus 64 is not a real number. Okay. For minus 64 to have a real square root, we would need a number which, when multiplied by itself, gave us minus 64. Now, we can't do that because, let's say what we thought was the square root. Let's say we have a possibility for the square root of minus 64 and it was positive. Well, that couldn't be the square root of minus 64 because a positive number times a positive would give you a positive result. That wouldn't give you minus 64. Okay? Couldn't be negative because a negative times a negative would also give you positive. Couldn't be 0 because 0 times 0 is 0. In other words, we need a number which, when multiplied by itself, gives you minus 64. And there is no such real number. Negative numbers, therefore, do not have real square roots. And for our purposes, we're only working with real numbers. We'll say that we can't take the square root of a negative number, Positive numbers will have 2 square roots. 0 has 1 square root. Okay, if you just see the radical sign in front of the number, that means the positive square root only, for example, like here, plus 3. It's not plus 3 or minus 3. Okay, if you want to indicate the negative square root, a minus sign has to precede the radical sign. Okay, now, there's a difference between that and somebody giving you this problem over here. If they say x squared is 9, what is x? Then it is true. X is 3 or minus 3. But if you see the radical sign with the 9, that means just the plus 3. Negative the radical of 9, that would be negative 3. Okay, now, the positive square root of 49, for example, is plus 7. The negative square root of 49 is minus 7. Okay, this is the same thing as saying the square root of 49, positive square root of 49 is 7, since 7 squared is 49. It's still following the same definition that I gave you before. The only difference is that I'm not writing out square root. I'm using the radical sign. The negative square root of 49 is minus 7. Minus 7 times minus 7 is 49. Okay, now what about something like the square root of 5? The positive square root of 5. We know that the square root of 4, positive square root of 4 is 2. What about the square root of 5? Now, the square root of 5 is what we call an irrational number. Okay, the real numbers, all those numbers that have decimal representations, can be divided into rational and irrational numbers. Now, rational numbers are those numbers that have decimal representations which either terminate or repeat. So, for example, you have 0.37. That is a rational number. It's a terminating decimal representation, or something like this, 0.333. The 3 is repeating. This is also rational. Strictly speaking, a definition of rational numbers can be, well, a rational number is a number that can be expressed as a quotient of 2 integers, where the denominator is not 0. You see, 0.37 can be written as 37 over 100, the quotient of 2 integers. And 0.3333 repeating, this is just going on like this, this can be written as 1/3. And if you don't believe this, you can, of course, this is 1 divided by 3. You can divide 3 into 1 using long division, and you will get 0.333 and so on. Okay, so rational numbers have decimal representations which terminate or repeat. They can also be expressed as a quotient of integers. Okay, the square root of 5, however, is not rational. Okay, it is a decimal. It has a decimal representation which never terminates and never repeats. It goes on forever. It's approximately equal to 2.2 something, and it goes on. It doesn't terminate. It doesn't repeat. It keeps going on forever. Non-terminating, non-repeating decimal. Okay. That's not that important to us. It's just that you don't have to have all of your answers coming out very nicely. The square root of 4 is 2, fine. The square root of 9 is 3, that's okay. The square root of 5 is a decimal, but that doesn't have to upset you. Okay, from the point of view of working with it, it'll be following the same rules that we'll develop for things like the square root of 4. Now, 2 rules that are very important for working with square roots. And these are really theorems. I'm not going to prove them, but I will verify them at least for some examples. Okay, 2 rules which will enable us to work with square roots and to simplify them. Following. If a and b are positive numbers, the square root of ab is the square root of a times the square root of b. Okay, I say the square root, I'm talking here the positive square root. A and b are positive numbers. The positive square root of ab is the positive square root of a times the positive square root of b. A and b have to be positive numbers, or else I would be taking the square root of a negative number. We've already discussed that. We're not going to be doing that. You can't do that in the real numbers. Okay, as a verification of this, rather than a proof, let us look at the square root of 4 times 9. According to this rule, this should be the square root of 4 times the square root of 9. Now, I picked that because it's something that we can work out. Okay? The square root of 4 times 9, of course, is the square root of 36. Now, 36 is a perfect square. The positive square root of 36 is just 6. The square root of 4 is 2. The square root of 9 is 3. And 2 times 3 is 6. So apparently, at least it works in this example. Now, this is not a proof, but at least it shows you that the rule seems to make sense. Okay, now this is for products. We also have a version of this for quotients. If A and B are positive numbers once again, and this time we're going to say B is not 0. Okay, if A and B are positive numbers, and B is not 0, the square root of A over B is the square root of A over the square root of B. That is, the square root of a fraction is the square root of the numerator divided by the square root of the denominator. This rule can be thought of as the square root of a product is the product of the square roots of the factors. This one, the square root of a quotient, the square root of a quotient, the square root of a fraction, the square root of the top over the square root of the bottom. Okay, and once again, we're not proving this, but if you wanted to see it verified for an example, we could work out the square root of 36 over 4. I want to show you that we do get the square root of 36 divided by the square root of 4. Okay, working this out. 36 over 4, of course, is 9. The square root of 9 gives you 3. Over here, the square root of 36, that's 6. The square root of 4 is 2. 6 divided by 2 is also 3. So apparently, it does work in this example. Okay, please be aware of the fact that I gave you a rule for products, I gave you a rule for quotients, I gave you nothing for sums and differences. It is not true okay. The square root of A plus B, however, is not the square root of A plus the square root of B. Also, the square root of A minus B is not the square root of A minus the square root of B. These don't work, okay? It doesn't work for sums. It doesn't work for differences. It works for products, and it works for quotients. These are okay. These are not true. Okay, now somehow people want to do it more when there are numbers involved rather than when they're just letters. For example, if you had the square root of 9 plus 16, that is not equal, much as it would be nice if it were, it's not equal to the square root of 9 plus the square root of 16. And we can easily, you don't need a proof to show something like this doesn't work. You just need an example that doesn't work. Okay, and that does it. It shows you that it's not generally true. You see, the square root of 9, that's 3. The square root of 16, that's 4. So you get 7 over here. On the other hand, 9 and 16 gives you 25, and the square root of 25 is 5. So clearly, you cannot break it up over addition. You can do it for multiplication and division, but not for addition or subtraction. Okay. Of the square root is the fact that the square of the square root of a number is just a number itself. Okay, if x is a positive number, or if it's non-negative, the square root of x times the square root of x is just equal to x. Okay, here I'm assuming x is non-negative. A non-negative number. For example, if I say the square root of 4 times the square root of 4, you could say, well, this is 2 times 2. That gives you 4. But that's only because these were perfect squares, and you could work it out. You shouldn't even have to think about it. The square root of 4 times the square root of 4 is simply 4. Okay, you could also make use of the rule we just had. The square root of 4 times the square root of 4 must be the square root of 16. Using this, the square root of 4 times the square root of 4 must be the square root of 4 times 4, the square root of 16, which is 4. But that's all roundabout work we don't need. Just remember this rule. Okay, it comes from the idea of the definition of square root. If you square the square root of a number, you just get the number itself. Okay, so if you had the square root of 5 times the square root of 5, even though I don't know, okay, say exactly what the square root of 5 is here or something like that, you don't have to make it the square root of 25 and get 5. Just the square root of the number times the square root of the same number gives you the number itself. It squares out and you just get the 5. The square root of 231 times the square root of 231 is 231. It doesn't matter that it's not a perfect square. Okay, you don't care what it is. The square root of a number times the square root of the same number just gives you the number itself. Okay, now it's going to be important for us to simplify expressions under a radical sign. We would like basically to keep the stuff under the radical sign as simple as possible. If something is a perfect square, we'd like to pull it out. Okay, in order to do that, we have to understand how square roots work. Let me show you some examples. In all of these examples, I will assume that x is non-negative. Okay, the square root of x squared is just x. In a more advanced class, when you consider the possibility of x being negative, okay, then you need the idea of absolute value here. But we're not going to concern ourselves with that right now. Just the square root of x squared is x, since x times x is x squared. And the square root of x to the 4th is x squared, since x squared times x squared is x to the 4th. This following the basic definition. What about the square root of x to the 6th? Okay, if you see what we're doing here, the square root of x to the 6th would have to be x cubed, since x to the 3rd times x to the 3rd is x to the 6th. You know, when you multiply, okay, you keep the base the same and you add the powers. Okay, so in general, the square root of x to an even power will be x to 1/2 of the power that it was originally. You'll have the power. Okay, now this is not to be confused with what you already know to be true, okay, of taking square roots of regular. For example, if you have the square root of 9, x to the 16th. You can break this up using the fact that the square root of ab is the square root of a times the square root of b. So this is the square root of 9 times the square root of x to the 16th. Now, the square root of 9, you write 3. It's the positive square root of 9. The square root of x to the 16th, you write x to the 8th. Okay. So for 9, you took the square root, but for 16, you don't take the square root of 16. Don't write 3x to the 4th here. Okay, you have the power, because when you multiply 3x to the 8th times 3x to the 8th, you get 9x to the 16th. X to the 8th times x to the 8th will give you the x to the 16th. So don't get carried away with yourself. Don't think it's 3x to the 4th. The square root of 9, that's 3. That's OK. But the square root of x to the 16th is found by having the power to get x to the 8th. OK, now, in this problem, this was like a perfect square. Everything was, you were able to pull everything outside of the radical sign. Now, very often we have in algebra problems that are sort of mixed. Part of it is a perfect square, and the rest of it can't be moved out of the radical. Let's try some of those examples. OK, let's say we want to work with the square root of 18. And we want to simplify it. By simplify it, I mean try to pull as much as you can outside of the radical sign. What's under the radical sign should be as small as possible. OK, now the trick is to factor 18, to break it up into a perfect square factor times some non-perfect square part. Now, 18 can be factored in a variety of ways. The way to do it here would be to make it 9 times 2, because this is the square root of 9 times the square root of 2, or 3 times the square root of 2. It's true that, for example, 18 is also 6 times 3, but that wouldn't help us anyway. In other words, what we're looking for is a perfect square factor of 18. So I would try 4, which is 2 squared, 9, which is 3 squared, 16, 25, and so on. Numbers like that. And I want them to be a factor. In other words, two things which multiplied give me, say, the 18. Okay? Even though, say, 18 is 16 plus 2, that doesn't help. This is not the square root of 16 plus the square root of 2, because remember, that rule doesn't work for addition. You can break up a product. The square root of a product is the product of the square roots of the factors, but as I explained earlier, you cannot break it up this way over addition. So you can't make this, say, 4 plus the square root of 2. It's not just to look for any old perfect square, but it has to be a perfect square factor. 9 is a factor and a perfect square. 9 times 2 gives you the 18. Okay, so this can't be used. Also, 6 times 3 doesn't much help because neither 6 nor 3 is a perfect square. So in this case, this is a way to simplify the problem. Okay, let's try a problem that has constants and variables under the radical sign. How about the square root of 12x to the 9th? If I say just square root, I mean the positive square root. Okay, we're going to try to factor 12x to the 9th. We want to break it up into a perfect square factor and then see what's left over. Okay, now, first we worry about the 12. Well, 12 can be thought of as 2 times 6. That doesn't much help us. 4 times 3, that's good because we have a perfect square factor. So we'll write that as 4 times 3. Now, x to the 9th, I'm going to rewrite as x to the 8th times x to the 1st. Remember, x to an even power is a perfect square. Okay, to take the square root of x to an even power, we just get x to 1/2 the power that we started with. Okay, so anytime if you have x to an even power, fine, you can put the whole thing into the perfect square part. If it's x to an odd power, well, you're always 1 away from an even power. So you pull off 1, and x to the even power is in the perfect square part. Okay, this is like the square root of a times b. We can break this up into the square root of a times the square root of b. Now, this is similar to the problem that we worked out a little earlier. So take the square root of 4x to the 8th. The square root of 4, that's 2. The square root of x to the 8th is x to the 4th. Okay, on 4, you took the square root. On 8, you halved it. Okay, 2x to the 4th times 2x to the 4th will give you 4x to the 8th. And this part cannot be simplified any further, so you get 2x to the 4th times the square root of 3x. Okay, let's try one more example. And of course, you can shut the machine off and try this one on your own. And turn it back on when you have finished. 50x to the 7th y squared. I want to take the square root of that. Okay, now, we're looking for a perfect square factor of 50. Okay, we try 4. That doesn't go in. 9, 16, 25. Okay, 25 goes into 50 evenly. So we get 25 times 2 for the 50. X to the 7th will make x to the 6th times x, and y squared, okay, that's an even power, so we can leave that alone. Okay, so for constants, most people don't have that much trouble with the constants. You're looking for perfect square factors, 4, 9, 16, 25, and so on. For an odd power, you pull off 1 and put it in the non-perfect square portion, and you keep the even power here, and if it's all even, you just keep it in this section. The square root of a times b, of course, now is the square root of a times the square root of b. Now, this you can remove the radical from because this is a perfect square. That's why you isolated it like that. The square root of 25 is 5. The square root of x to the 6th is x third, halving the power. The square root of y squared is y times the square root of 2x. 5x cubed y times the square root of 2x. And that brings us to the end of the tape.